Welcome to The Explainer. I'm your host, your strategist for today. We are taking the fascinating invisible world of static electricity and transforming your foundational knowledge into absolute gold standard Cambridge examination evaluation. We are looking specifically at the 0625 physics syllabus. Listen, static electricity is a topic where examiners routinely separate the top-tier A-star students from the rest of the pack. I want you to imagine you are sitting in that exam hall right now. You can hear the clock ticking, the pressure's on. You flip the page and you see a 4-mark question on electrostatic charging. I want to introduce you to two students taking this exact exam right now, Alex and Sam. Alex is our classic overthinker. Alex overloads the page with raw physics facts, dumping everything they memorized, but provides zero actual analysis of the specific question being asked. Result? 1 out of 4 marks. Then we have Sam. Sam is rushing against the clock, writes a single sentence, hoping it covers the basics, and misses the core requirement of the command word entirely. Another strike of the examiner's red pen. Our goal today in this explainer is to completely erase those red marks and replace them with green check marks. We are going to build your ultimate physics success blueprint, step by step. Let's get into it. So here is the structured roadmap for our journey today. Don't worry about taking notes just yet, just absorb this. First, we'll look at the spark of static, the everyday phenomena you've definitely experienced. Second, we shrink all the way down inside the charged atom to see the actual hidden mechanics. Third, the rules of attraction will govern how these invisible forces interact with each other. Fourth, we will contrast conductors versus insulators, which is a massive trap for students. Fifth, we'll visualize the unseen by mapping electric fields. And finally, our capstone, the real secret sauce, mastering exam command words. Okay, let's dive into section 1, the spark of static. We're talking about everyday, completely invisible forces. Let's look at a really classic Cambridge scenario. Why do you get a shock from a simple metal door handle after walking across a nylon carpet? What's absolutely fascinating about this scenario is the hidden physics taking place in that everyday, slightly painful annoyance. Now, if Alex were answering this, Alex might write something like, because there is electricity in the door and humans conduct electricity. Boom, red pen. That's way too vague for Cambridge. Sam might write, friction makes a shock. Again, red pen. It completely misses the actual mechanism. The real answer, the one that extracts the marks from the examiner, lies in understanding that this is a detailed story of friction, buildup, and sudden release. As your shoes rub against those synthetic carpet fibers, a literal, physical transfer of microscopic particles is occurring. Without even knowing it, you become a walking, talking battery of stored charge. And when your hand gets close to that metal door handle, which is a conductor, that stored charge violently jumps the gap. Zap! You feel physics. Now take a look at this. Notice the child on the trampoline. Their hair is standing on end, literally reaching for the sky. Why is this happening? Well, bouncing on the synthetic material of the trampoline creates a massive amount of friction. That friction generates an invisible electrostatic force all over their body. Each individual strand of hair becomes charged with the exact same type of static electricity. And as we will soon see in our core rules of physics, identical charges do not want to be anywhere near each other. They push away, they fiercely repel. This image is the absolute perfect visual anchor for you to remember the concept of frictional charging. Keep this image in your head when you're in the exam room. Moving right along to section 2, inside the charged atom, we need to identify the mover. We have to begin with the absolute default state of the universe, and that state is neutral. By neutral, we mean having no overall positive or negative charge. You see, atoms start out perfectly balanced. It's quite beautiful, actually. In their center, right in the nucleus, they have positive charges. Orbiting around the outside, they have an exactly equal number of negative charges. Positive equals negative, so the net result is 0. Everything is calm, everything is perfectly neutral. To create static electricity, to get that spark, we have to violently upset this delicate microscopic balance. All right, listen up, because there is a crucial, absolutely critical distinction right here where thousands of students lose incredible amounts of marks every single year. Protons carry a positive charge, and they are heavily Loctite inside the nucleus of the atom. They do not move during static charging. I'm going to repeat that because it is vital. Positive protons never, ever move. Electrons, on the other hand, carry a negative charge, and they are only weakly held on the outside of the atom. Therefore, the golden rule you absolutely must memorize right now is friction transfers only electrons. When you rub a plastic balloon on your sweater, the friction provides enough physical energy to literally rip those weakly held negative electrons off one material and deposit them onto the other. If an object gains electrons, it becomes negatively charged. If it loses electrons, it is left with a massive abundance of positive protons, so it becomes positively charged. If you ever write protons transferred in your exam, you immediately automatically lose the mark. Only electrons move. Got it? Good. Before we continue, subscribe to our YouTube channel Ace the Exams at actheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Now, you might be wondering, just how tiny is this charge we're talking about? Well, a single electron has a charge of negative 1.6 times 10 to the power of negative 19 coulombs. The coulomb is the standard unit of electric charge. That number is unimaginably, mind-bogglingly small. To put it in a perspective you can actually grasp, it takes more than 6 million electrons to make just one single coulomb of charge. Think about that for a second. When you get zapped by a door handle, literally billions of these tiny negative particles are flowing right through your skin in a fraction of a second. It's a massive microscopic migration. All right, section 3, the rules of attraction. Let's look at these invisible forces. Let's act as an examiner for a minute, analyzing a classic laboratory experiment. You'll see this in paper after paper. Notice the hanging rods in this experiment setup. We have a plastic rod that's been rubbed with a cloth. It's hung delicately in a cradle so it can spin completely freely. When we bring the very cloth we used to rub it close to the rod, what happens? The rod swings right toward the cloth. It is strongly attracted. But, and here is the kicker, if we take a second, totally identical plastic rod, rub it with an identical cloth, and bring that second rod close to the first one, the hanging rod aggressively swings away. It is repelled. By observing this exact behavior, physicists deduced that rubbing the rod and cloth gave them opposite charges, which clearly attract each other. But two identical rods, rubbed the exact same way with the exact same material, must hold the exact same charge and therefore they repel. And this brilliantly illustrates our next foundational rule, what I like to call the golden rule of electrostatics. Like charges repel, opposite charges attract. It is that simple, but you have to apply it perfectly. Two positive charges will push apart. Two negative charges will push apart. But a positive and a negative, they will snap together immediately. Think back to the child on the trampoline we looked at earlier. All that bouncing stripped away electrons, leaving all the individual hairs with the exact same charge. Because like charges repel, every single individual hair was frantically trying to get as far away from its neighboring hair as physically possible. That is exactly why they stand up in every single direction. It's the golden rule in action. Let's shift gears to section 4, conductors versus insulators. Material matters. Why do some things shock you and others don't? The difference lies entirely in their atomic structure. Let's compare them. Conductors, primarily metals like gold and copper, have what we in physics call free electrons. These electrons are like tiny nomads. They can wander easily and freely between atoms. If you try to charge a copper rod by rubbing it while holding it, sure, the electrons are transferred. But because copper is a brilliant conductor, those electrons instantly flow straight through the metal, through the moisture and sweat on your hand, straight down your body, and safely into the earth. The charge dissipates instantly. No buildup, no shock. Insulators, on the other hand, are nonmetals like plastic, glass, and rubber. Their electrons are locked down. They are tightly bound. They absolutely cannot flow. So, when friction dumps extra electrons onto a polythene rod, those electrons are trapped right exactly where they landed. They physically build up, creating that powerful stationary electrostatic charge. This is the transformation phase, guys. Understanding this difference is exactly how we turn red pen marks into green check marks. Actually, here is a truly fascinating historical fact that directly ties into this concept. The ancient Greeks actually discovered static electricity thousands of years ago using this exact material you see here, amber. Amber is just fossilized tree resin, as you can see perfectly with this trapped insect. But what's crucial is that amber is a fantastic, completely natural electrical insulator. The Greeks found that if they rubbed amber with animal fur, it could magically attract tiny pieces of straw or a feather. They had absolutely no idea about protons or electrons, but they observed the exact same physics we're studying for your exam today. In fact, the Greek word for amber is electron, which is literally exactly where our modern word electricity comes from. How cool is that? Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at actheexams_IGCS to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to @theexams_IGCS and turn on all notifications so you never miss our weekly exam strategy sessions. All right, Section 5, Mapping Electric Field, Visualizing the Unseen. So, what exactly is an electric field?
It is formally defined as a region of space in which an electric charge will experience a force. Think of it as an invisible aura of influence surrounding an object. A charged balloon doesn't actually need to physically touch your hair to make it move. The hair simply needs to enter that balloon's invisible electric field. The closer you get, the stronger the field and the stronger the force.
Let's dive into an interactive workshop right now. Let's actively scan these diagrams. This is an absolutely essential data scan skill for your exam. I'm putting a mental 60-second timer on you. Look at the isolated charges on the left. Notice the direction of the arrows. They always point away from the positive sphere and strictly toward the negative sphere. Why is that? Because field lines are strictly defined by physicists as showing the direction of force on a hypothetical positive test charge. If I dropped a tiny imaginary positive particle near the big positive sphere, it would be repelled, pushed outward. Hence, arrows point out. Now look really closely at the diagram on the bottom right. Two oppositely charged parallel plates. Notice how the lines between the plates are perfectly straight, evenly spaced, and completely parallel. This is crucial. This represents a uniform electric field, where the force is exactly the same strength everywhere between those plates. Scanning and extracting these core trends rapidly from a complex physics chart or diagram is exactly what separates our A-star students from the rest. Now for our final, most important section. Section 6, Mastering Exam Command Words. This is pure strategy. The Cambridge syllabus uses very specific command words, and treating them equally is a fatal error. Let's do a find the flaw challenge. State means express in clear, concise terms. It's a quick fact retrieval, usually worth just 1 mark. You don't need a massive paragraph for a state question. But explain? Oh, this is the heavy hitter. It means you must set out the reasons. You must provide the why or the how using hard scientific evidence. To conquer an explain question, top students use the PEEL framework. PEEL, point, evidence, explanation, link. You make your point, you cite the evidence from the specific scenario in the question, you provide the explanation using core physics principles, like electron transfer, and you link it back to the final result they asked about. Let's look at a real past paper scenario. A student investigates charging polythene by friction. She takes 2 identical strips, rubs each with a cloth, holds them together, and they move apart. The exam asks, explain why the strips move apart. Worth 2 marks. If Alex wrote, the friction makes electricity and the strips hate each other so they repel. 0 marks. That is a deeply flawed paragraph. It completely lacks proper scientific terminology and explains 0 mechanism. If Sam wrote, like charges repel. 1 mark. Sure, it's a correct factual statement, but it completely ignores the command word explain because it doesn't state how they got those like charges in the first place. We need to use our PEEL framework to secure full marks. We are going into speed writing mode. Here is your ultimate template for the perfect PEEL paragraph on this exact question. Step 1. The explanation of mechanism. The physical friction transfers negatively charged electrons from the cloth to the polythene strips. Step 2. The point. Because both strips are identical polythene, they both gain the exact same negative charge. Step 3. The link to the outcome. According to the rules of static electricity, like charges repel, which forces the strips to move apart. Do you see the massive difference there? We didn't just state a fact. We traced the physical, microscopic journey of the electrons due to friction, resulting in a measurable physical force. That is a gold standard, bulletproof answer that an examiner will gladly and quickly award full marks. That is your blueprint. Now, let's look at how this applies to real-world engineering and ethical scientific testing. Let's call this shocking shopping. A store manager has a huge problem. Her new polypropylene carpet is giving customers painful static shocks when they touch the metal stair banister. She desperately needs to test new carpets. But you are her highly paid scientific consultant. You can't just have humans scuff their feet and touch a metal pole all day. That's highly unethical testing. Instead, you apply your newly mastered physics framework. You propose rubbing a standardized insulating block across different carpet samples with a strictly controlled amount of friction, and then measuring the static buildup using an electronic balance to gauge the force of attraction on a charged sphere. You've just taken textbook physics and solved a real-world dilemma safely, systematically, and scientifically. This brings us to a profound summary, beautifully captured in this quote. If all the objects around us were made of charged atoms, we would live in a shocking world. Think about everything we've covered today. Our entire universe relies on a delicate, perfectly neutral balance. The positive protons, hidden completely deep within the nucleus, perfectly balance the chaotic, weakly held negative electrons orbiting on the outside. It is only when we intentionally introduce the brute force of friction, specifically on insulating materials that trap those moving electrons, that we unleash the powerful, totally invisible electric fields that govern the rules of attraction and repulsion. We have 3 rules that guarantee top marks: command word decoding, Peel framework application, and time management. Students who implement these physics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly explainer sessions. So I leave you with this final provocative thought. Could the simple, annoying act of shuffling your feet on a new carpet and getting zapped actually be the key that fundamentally changes how you understand the deepest invisible forces holding our entire universe together? Every single time you feel that tiny spark, you are literally interacting with the fundamental building blocks of reality. Here's your final reminder: subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCS to excel in your Cambridge examinations. Subscribe right now to at acetheexams_IGCS and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for physics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams, your Cambridge success starts here.